Yeah, well, yeah, that's what
Okay, you got a convex mirror. An object is located 20 centimeters, and the image is at 5 centimeters. Determine the focal length of the mirror and the radius of the mirror, radius of curvature. Yeah. So, convex mirror, the object's at 20, and the image is at 5. What's the focal length, and what is the radius of curvature? No. What's up? All right. So you got an object, as you walked in, you got a convex mirror, the object is 20 centimeters and the image is at 5 centimeters. How did I know how to draw this thing? Yeah, we're taking the assumption that our light generally starts from the on the left side and heads towards the right. So that's what we're thinking about. So the object distance D0 is indeed a plus 20 centimeters. What about the image? How did I know to draw it on the other side of the mirror? Turns out that convex mirrors only produce virtual images. So that's something that should have come to mind when the word convex came into your being. You say, oh, convex mirror, that only produces a virtual image. If it's a virtual image, it's a negative distance. So I should write that dI is actually equal to a minus 5 centimeters. Convex mirrors only produce virtual images, so therefore dI is negative 5. And now we're going to go ahead and put that into our mirror equation. 1 over dO plus 1 over dI is equal to 1 over F. And we'll find F that way. 1 over 20 plus 1 over minus 5 is equal to 1 over F. And we find out that F is negative 6.667 centimeters. And R is equal to negative 13.33 centimeters. Everybody happy with that? So for a concave mirror, the focal length is 20 centimeters. The object is at 24 centimeters, just outside the focal length. Find the image. Tell me if it's real or virtual, upright or inverted, larger or smaller. Answer those questions. So by the diagram, I found out that it's real and inverted. And it's going to be larger. Is that what you got? So diagrams are kind of useful. We can do some things pretty quick. See if we can put the numbers in here. 1 over di is equal to 1 over f minus 1 over do. 1 over 20 minus 1 over 24. Says that di is equal to 120 centimeters. That tells you that it's real. Now we get the magnification, which is minus di over do, negative 120 over 24, which gets negative 5. So we can say that it is inverted and 5 times bigger. Are we okay with that? Is that all right? All right. Yeah, let's make a fun question out of it. The object moves. The object moves to a distance 22 centimeters in a time of 3 seconds. So let's calculate the average speed of the object. And also calculate the average speed of the image. So the average velocity of the object is straightforward enough. It's moving towards the mirror. There's actually a minus on there. I can't do math today. What about doing the image velocity? The average speed of the image. Well, that will be di final minus di initial divided by delta t. And so now we have to figure out where that second image is. When the object moves to 22 centimeters, where is the image? Well, you got to do that over again. So 1 over di final is equal to 1 over f minus 1 over do final. What was RF? 20? RF is 20. Says that it's 220 centimeters equal to di final. So 220 centimeters minus 120 centimeters divided by 3 seconds gets us 33, right? 33.3 centimeters per second, or 0.333 meters per second. But now we also want to talk about the direction. This happens to be a positive number. So since that number is positive, we want to think about that as going away from the mirror. So as the object runs towards the mirror, the image runs away from the mirror. Well, at least in the concave case. What about in the plane mirror case? Since you have experience with that, if the object runs towards the mirror, which way does the image run? Towards the mirror also. This one goes the other direction. It's kind of fun. What happens to the image? What happens to the image when the object is at F for a concave mirror case? So where is the image? What is that telling you? Pardon? Nope. Well, there is an image. That's telling you it's someplace. If 1 over di is equal to 0, then di must equal 1 over 0, but that's not really allowed. So what you really want to think about is what over something gets you 0? Infinity. Therefore, we think of di as equal to infinity. The object is at infinity. The image is at infinity. What does it look like? Kind of helps to draw that picture. So here's the focus, and we're going to put the object right at the focal point. And we're going to say that paraxial rays go out through the focus. And we're going to take another one out, and it goes out. And it turns out that these two rays are parallel. So you would think that they never meet except when they're infinitely far away. We kind of that's what the images of the image is infinitely far away. The image is also infinitely big, and it's upside down, infinitely big and infinitely far away.
I mean, infinitely big, it would be okay up here. I guess let's say that you're extreme here with the like gigantic or something.
Yeah, no, this is where this whole view of two-dimensional optics kind of falls apart. It doesn't really make sense with things like this when they get out to infinity. So, but you can play around with the math and you can try these things, and that's what you would get. So we do kind of use this idea. We just say that the image is infinitely far away. And the image and then you just go on. Yep. What to do with it. All right. Enough of mirrors. Any leftover questions about mirrors? You have 3 types of mirrors. You'll want to make a note sheet of their various properties. Convex mirrors, you only get virtual images. Plane mirrors, you only get virtual images. Concave mirrors, you can get real or virtual images. The radius of curvature for a plane mirror, is that 0 or infinity? It's flat. So what's the curvature? You would tend to think flat means no curvature, therefore there's for 0 radius of curvature. Actually, we mean infinite radius of curvature for a flat mirror. So you want to think about those 3 different cases, where the images are, where the what the sign conventions might be. So concave, we're going to have r greater than 0. Convex, r less than 0. Plane, r equal infinity. Any leftover questions about the sign convention? Just to refresh your memory, sign convention is the object distance is positive if the object is on the side of the incoming ray. I don't think we're going to run into any cases where it's different than that, but never say never. Something might show up. The image is on the image distance is positive if it's on the side of the outgoing ray. Similar, the radius of curvature is positive if it's on the outgoing ray, and of course, whatever R is, F has to be the same. If it's positive, there it comes positive. Yeah? Andrew? For mirrors, yes. Our incoming and outgoing rays on the same side for mirrors. Yes. Because we can use this exact same sign convention for lenses as well. And then we don't have to remember two sign conventions. That's the really important thing of getting this one straight. All right. So we got into a lab yesterday about refraction. And so we have a surface. All angles are measured normal to the surface. So here's your normal. Normal meaning perpendicular, right? You remember that. If our incoming ray is on this side, the angle theta incoming, this side has an index of refraction of N1, this side has an index of refraction of N2, then depending on the relationship, whether N2 is bigger than N1 or N2 is less than N1, you'll get some bending of light. And if N2 equals N1, they would be the same. If N2 equals N1, yes. Okay, so let's think about that as the path where nothing happens. And it goes in this direction if N2 is greater than N1. And it goes in that direction if N2 is less than N1. So the light, you could phrase this as the light either bends towards the normal or away from the normal. How would you word those sentences? If you wanted to make yourself notes so that you knew you understood this. Say when N2 is greater than N1, the light ray bends towards the normal. It's bending towards the normal relative to the path that nothing happened. So if it was going like that, it goes like that, towards the normal. So,
when you like think about that, I don't know if you think about this at all. Or is it something like I don't know if that's related.
Typically, you can also think of it, it's often described in terms of, not in terms of density of the material, but effectively the index of refraction does measure something like density of the material. What you want to be able to think about is, just to keep it straight, which way does the light bend? And so let's do a quick little example problem. Then we'll take a glass where n equals 1.5, and outside of it, it's air. And for air, we're going to take it to be 1. And we have an incident light ray coming into our piece of glass like so. We need to draw our normal. And our incident ray is at 30 degrees to the normal. At that interface, what happens to that? What is the refraction angle? Or you're using Snell's law. Theta 2 is equal to the sine inverse of n1. 30 degrees divided by n2. And we find out that it is 19.47 degrees. Is that what you got? How do you draw that? Okay. Again, it's think about the path where nothing happens. And of course, we're measuring the light relative to the normal. So here's our refracted angle, theta 2. And this is the 19.47 degrees. And that would make sense to you because N2 is bigger than N1, so you know it bends towards the normal. Easy way to remember it. Okay, this light keeps right on going. Gets to the other side of the glass. Now what happens? Need to draw the normals again. There's your normal. Does anyone have any questions about what the normals mean? All right. What's that incident angle for that ray on the other side of the glass? The incident ray. A little geometry would tell you that this angle, alternate interior angles, they're the same. This is also 19.47. And as it goes from the glass back into air, n is equal to 1. Here's where you have to start finding a way to keep things straight. You might want to call this theta 2. And how do we want to draw that one? That's the path where nothing happens. And now we're going from n2 of 1.5 into an n of 1. So it must go away from the normal. And so you would draw it like so. And we would call that, where I've been numbering them, I would call that theta 3. Now I would construct Snell's law for that second interface as n2 sine theta 2 is equal to n3 sine theta 3. And by the same work that we have before, we would have theta 3 is equal to the sine inverse of n2 theta 2 over n3. And when you do all that math, you should find out that this comes out to be 30 degrees. Are you okay with that? Feel up to a little geometry? Okay, we'll give it a shot here. Notice what happens to these two rays. It has been shifted. The two rays are parallel. They're not coincident. So let's go ahead and see, let's go ahead and say that the thickness of the glass is, well, let's say 5 millimeters. If the glass is 5 millimeters thick, how far apart are the outgoing rays? There's our chunk of glass. And our incident angle is 30 degrees. And then it refracts at 19 degrees. And then it refracts again back to 30 degrees. And the idea was that this ray, if there was no glass there, and this ray, because of the glass, what we'd like to try and do is come up with that distance. The two paths are parallel to each other, but how far apart are they? So the question is drawing a bit of geometry in there. Let's see if we can define the angles and whatnot. Let's give it a shot. That's what we're looking for, that distance. You know that this angle is 19.47. You know that that angle is 30. Do you see any way of getting there? Well, I guess what I would suggest is a couple of things that show up. Let's see if we can analyze this little triangle right here. And what we need is the angles, right? Is it believable that this angle is our 30 degrees? How would we even show that? Well, we know that angle is 30 degrees, right? And if that's 30, then this one must be 60. So the other one is 30. Yes. Okay. Not so bad. So now we've got a 30, 60, 90 degree triangle. I'm going to blow up the triangle just a little bit so we can see it a little bit better. 30 degrees. What we're trying to find is this distance. We know that angle. And we would be so happy if we could just figure out what this distance is. I'm going to call that A, the hypotenuse of this triangle. And then we could say that D is equal to A times the cosine. Well, cosine is going to be D over 30, right? So 30. So we're toast done if we can just figure out what the hypotenuse of that triangle is. And now just a little bit more geometry and we've got it. All we need to do is figure out the total distance here. Go away. We can figure out that one. And we need to subtract off that little chunk of that one. Okay. So we know that this is 5 millimeters. This is 5 millimeters. That's 30. So tangent of 30 is equal to I'm going to call it y1 over 5 millimeters. We'll call that y2. And the tangent of 19.4 equal to y2 over 5 millimeters. And then A, the number that we want, is equal to y1 minus y2. Which implies that I get for y1 point. I'm going to write it as 2.89 centimeters for y1. And y2 is equal to 1.76 centimeters, therefore A millimeters. What am I doing? It's from millimeters, sorry. And finally, D is equal to D is equal to 0.979 millimeters. This is mainly just an exercise in showing you that you will have to do some geometry, and you just have to be a little bit careful with it and be creative and see what you can do, but just work your way along and do it and make sure all your relationships are correct. Any leftovers? So this gives you some idea of why a window works, right? When you look out a window, the fact that the window has two sides that are planes, what you're seeing, all the light rays are parallel to each other, but they're offset a little bit. When you look out a window, it'd be really weird to have windows if that wasn't the case. And actually, if you look at really old glass, like glass in the really old apartments in San Francisco, where the glass has started to wave, and planes aren't parallel anymore, and it doesn't work anymore. You get the little wavy images. All right. Okay, we're going to go from a high index of refraction in 1 is equal to 1.4 into a lower index of refraction in 2 is equal to 1.3. There's our normal. And we're going to come in like so. There's our theta 1, our incident angle. Draw the outgoing angle. Just see if you can get the right idea for the outgoing angle. How did you draw the outgoing angle? Towards the normal or away from the normal? Away from the normal. Okay. Draw another ray, but it's coming in at a bigger angle. We'll call that theta 1 prime because it's still incoming. What about that second ray, which comes in at a larger angle? How is its outgoing ray going to be related to the first one? You said the first one was doing this, right? And then you must have said that the second one is doing that. Is that what your drawing looks like? Yes? Okay, that should suggest something interesting. Hopefully. Does it suggest anything at all? Refracted back, not exactly back, but there's some angle where the outgoing ray is parallel to the surface. If I make it just a little bigger, it's parallel to the surface. How would you determine the angle at which the outgoing ray is parallel to the surface? See if you can find it. You got numbers, you can actually come up with a number. What angle should I draw that will give me an outgoing ray parallel to the surface? So if I were to draw it, I'll draw it like so. Looking for a ray that would give me this result. Sine of 90 degrees without using your calculator. Find out that sine. Find out that theta 1 is equal to the sine inverse of n2 over n1, which in this case 1.33 divided by 1.4. And you find out that that's 71.8 degrees. And because this is a rather special angle, we will now call this one theta sub c for theta critical. The critical angle for total internal reflection. That is no transmitted light. And if you want a way to think about it, n1 sine theta 1, n1 sine theta critical is equal to n2 sine theta times sine 90. This concept is total internal reflection.
So we add higher than theta critical, but then it'd be coming off of that. And it would go like theta critical, just go straight on the surface. And that would reflect off.
Bounces back in. And then it's just reflection. Right. Got it? Seems too easy. So here's another interface of two different media. And I am now looking for the critical angle for total internal reflection. What angle should I come in at to get total internal reflection? And so you do just what we said before. N1 sine theta critical is equal to N2 sine 90 degrees. And you could say that the sine of theta critical is equal to N2 over N1, which is equal to 1.7 over 1.2. And you say, wait a minute. That breaks your calculator, gives your calculator a little bit of a headache there, right? 1.47. We say the sine doesn't go up that high. The sine stops at 1, yes? So what that tells you is that this is not possible. So what's the difference between these two cases? There was this case where it was possible, and the second case where it was not possible. Is there something that we can learn from that to figure out what the procedure is? Andrew? N2 has to be less than N1. Okay, when N2 is less than N1. Have you ever experienced total internal reflection? Andrew, how do you experience it in fiber optics? That is how they work, but do you have any experience with total internal reflection? You probably do. Walls. It's a good stretch. Okay, we have to have the second index of refraction less than the first one. And the index of refraction of air is 1, right? So if you're going to experience total internal reflection, you have to be in a medium where the index of refraction is greater than 1. Have you ever been in this medium? Water in a pool, yes. So if you've been underwater in a pool, and if you ever looked up, you've experienced it. So here's our air, and here's our water. And here is you're looking upwards. Not up. So you're looking upwards. And if you look straight up, you can see straight up. That's just fine. So if this is your eye here and you're looking straight up, you can see whatever is directly over your head and you're under the water. But if you look off at this angle, and in this case, N of the water is 1.33, and the N of air is equal to 1. And if you look at this particular angle, you will see, well, that particular angle, after that angle, what you see is it looks like a mirror. You look up and you see you're looking at a mirrored surface. And that mirror, what it's reflecting is, of course, just the bottom of the pool. In most pools, the bottom is really whitish, so it looks kind of white, or kind of mirror-like. What angle is this critical angle? .8 degrees. Theta critical is equal to 48.8 degrees. So if you look off at an angle that's 49 degrees, you can't see out. But if you look at an angle that's 47 degrees, you can see out. Okay. Now let's talk about genetic adaptations using this process. Kind of fun to think about. Here's our water, and down in the water is, of course, our little fishy. There's our, I'm not very good, thinking of a little type of fish. And the little fish looks up. And it looks up over here, and it looks up over there. And of course what that little fish is looking for is birds. Because birds eat the little fishies. I'm in trouble with my birds today. The question is, does that fish see all those birds? Well, let's think. So the fish, how is this refraction going to work? The fish wants to see this bird here. The fish looks in this direction, and when the light gets to the surface, it refracts. So actually, since the light's coming off the bird, the light path is actually going like that into the fish's eye, and that fish can see that bird. Sure, just fine. We tried that game with the other one. Light comes in like so, refracts, goes into the fish's eye, and yes, the fish can see that bird just fine. If we take the third one, coming along just about parallel to the water, and it refracts along the critical angle, and it goes into the eye. So yes, the fish can see the whole upper hemisphere. Perhaps a genetic adaptation. Fishes want to know where birds are. So the fish can see 180 degrees by looking in a cone of how much? 48.8. So this cone that the fish has to look in has, when we talk about cones, we always talk about the half angle of the cone. And that is the critical angle, which is going to be 48.8 degrees. Is we're going to take this as air is equal to 1 and water is equal to 1.33. Another example, fiber optics. If you're underwater, you can actually see everything. You just don't usually spend that much time looking at it because you run out of air pretty quick. You can't hold your breath that long to figure out who's standing by the side of the pool waving at you, but you could see them. And the other problem with us humans being underwater looking at it is that our brains are not used to registering the images, and they're distorted. So that's why you would not be recognizing it. But if you spend some time, you could learn how to recognize those images. And in the camera world, this is called a fisheye lens for that reason. You get the very large picture, but it's distorted. Fiber optics. How to get Netflix, right. Great uses for fiber optics here. We have in, let's just take it at 1.5, and here in is equal to 1. Our fiber optic in air. Actually, fiber optics typically have a cable coating them to help with this process, but we won't go into that one. We're going to have a simple fiber optic. And the idea is that our light source, which is our little laser beam, it shines a light into the fiber optic with our little pulse of digital information. And of course, it's going from n equals 1 into n equals 1.5. So let me make it a little bit bigger, and then it refracts this way. And if the cable is set up just right, it bounces off of here in a reflection. Goes down here, bounces off this one, makes another reflection, bounces off that one, and it reflects. It doesn't go outside. As long as all of these interactions are larger than theta c. Larger than the critical angle. And what's interesting about fiber optics is that even if this thing is a bent tube, you can still do it. Hence the name of these things is sometimes referred to as light pipes. So here's our ray. Our incident ray will come in like that. It will refract and hit that one. And then it'll go off at an angle like so. And then it'll go off at an angle like so. Go off at an angle like so. And again, this works as long as these angles are larger than theta critical. Of course, there would be different angles this time because of the curvature. As long as those angles are bigger than theta critical, the light will stay in the pipe. Yeah. Questions?
How did they figure out that from the screen?
I don't know when they figured it out, but I guess it was probably about the time, probably as they were developing plastics. Because it's the matter of getting the fiber that you could actually bend conveniently. The early fiber optics were actually probably chunks of glass, but glass is a very impractical thing to set up as a wire because you can't bend it. It breaks too easy. So it's probably once they started developing the plastics that they came up with this idea. All right. Okay, when the index of refraction is a function of wavelength, this is the second lab, or actually it was the first lab we did the other night. First part of it. That is, here is our piece of glass. And now we need some kind of artificial idea for how to sort of make this work. And so what I'm going to do is bring in what I call bichromatic light. Light of two colors, yellow and blue. Lambda 1, lambda 2. Lambda 1 will be the yellow, well, we'll call that 580 nanometers, and lambda 2 will be the blue, we'll call that 450 nanometers roughly. And this is N is equal to air. And this is glass. And now we have N for lambda 1 being 1.6. And N for lambda 2 equal 1 point, I'll exaggerate it, make it work a little bit better, 1.5. Sorry, I want to do it a little bit differently because the typical it decreases as we go to longer wavelengths, so I'm going to do it the other way around. All right. And our simple question is going to be, at what angles do these two light rays emerge? Well, yeah, actually, let's not make it quite that difficult. Or actually, that would have been quite that easy. Let's say, what angles do the two light rays? 30 degrees will be our incident angle. Now, what angles do these two light rays refract in the glass? There you go. Now it's easy. And then the one was 1.6. I confused myself. Hang on a second. I did confuse myself. I do want to change that back to the other way I had it. It decreases with wavelength, increasing wavelength. Did we get those numbers? Okay. So just to emphasize this one last time, here's our surface. So our bichromatic light ray comes in at 30 degrees. And then it splits up into two parts. (18.2 and 19.47). This is the 18.2. That's the 19.47. Doing okay with these? In terms of wavelength, which one was which? Which one was the shorter wavelength? Which one was the longer wavelength? The longer wavelength is the bigger angle. This is lambda, what do they call it, 1 or something? Lambda 2, lambda 1, 580 nanometers. And the other one was lambda 2, which was 450 nanometers. Okay. So can you put together a way of remembering this? Steph almost was going in a direction. Bigger wavelength means bigger angle. That works pretty well. It would seem straightforward to me. That's not the way it usually is phrased, however. Shorter wavelength. Shorter wavelengths bend more. Or longer wavelengths refract less. Either way. The problem is when you're thinking about this, you have to be careful of what you're referencing to. And so there's two obvious things to reference. One is the normal, just like we wanted to do in that picture. Say that longer wavelengths make a bigger angle, and it's correct if you say to the normal. And shorter wavelengths make a smaller angle to the normal. Just remember to include what you're referencing. But this particular statement, which is in most textbooks, is not talking about the normal. It's talking about with reference to the undeflected path. So now you can see that the longer wavelength has a smaller refraction. We never calculate that angle, by the way. So anyway, when you're thinking about these, just be right careful. Make sure you know what you're referring to. All right. That's actually a good place to stop and take a break. We'll take a break a little bit early. We're going to look at these when we get back. Some of them have to do with mirrors, and some we haven't got the lenses yet, but we will. But to start on these, the first couple have to do with mirrors. There's more where we can take a break and we just take a mirror population. So take about 15, come back at 7:40.
My baby. Rolling right now. You know what you should get from stress? Yeah. Doesn't matter what part it's stress. And if you want to buy it, stress. It was a lot of blood. But I mean, once you put it in, it's just like, it's relaxed. You don't have to worry about it. Only get right. It's just nice. It's easier to have it. I mean, I probably especially the thing where it's just like, yeah, yeah. Yeah, well, you said we hope pretty bad. Oh yeah, yeah. You got a 50 man. No worries about it. I can give on it. Yeah. Yeah. Yeah, like hours, like with your body. A little bit friendly, and rush.
Make some progress. If you have, that's good. But if you haven't, make some progress. Time to focus on the physics now. So it's a smaller inverted image. It's not what the question asks yet, but it's useful to figure that stuff out. Real or virtual? Real. What does the real mean? But what does it mean to call an image real? If I say I have a real image, what can I do with that? There's actually light rays there. If I put a piece of paper where that image is, they will focus the light rays on that piece of paper, and you'll be able to see it. Whereas if it was a virtual image, the light rays aren't there. It just acts as if the light rays go there. All right. That wasn't too bad. Any leftover questions on number 1? Let's move on to number 2. Okay, the image is to be upright and 1.5 times bigger. That should suggest to you that let's think about the magnification equation. Therefore, we find out that the image distance is minus 1.5 times d0, do, which is minus 45. So here's our image. When I unscramble that, I find out that the focal length of this mirror is 90 centimeters. Not asking for it, but we might as well go ahead and get it. The radius of curvature is 180 centimeters. Where is the focal point? We'll really put it on this diagram. So which side is it on? Right side or left side? Left, yeah. 90s, it's about, our focus is way out there, it's our focus. Questions? This second question is kind of typical of how these word problems get a bit more complex. We've got to pull together all this information. It's not going to be a direct little problem. You're going to have to pull a few things together in order to solve some of these problems. Any immediate questions? All right. Moving on to number 3. light in air. Ooh, refraction, yes. Oh, this one's kind of a strange one. So here a light beam enters at 56 degrees, and part of it is reflected, and part of it is refracted. And all they tell you is that this angle happens to be 90 degrees. And of course the question is about what is the index of refraction, which means, okay, you need to get this angle, theta 2. If you can figure out what theta 2 is, you got it. So obviously you're going to have to do something with that reflected part. The law of reflection tells you that this one is also 56 degrees. Now you see your nice little favorite thing, geometry. 56 plus 90 is equal to theta 56 plus that equals 180 degrees. Which is what, 34. .48 roughly. questions? Crown glass into water. Real easy. .61 degrees. Question. Done that one too many times. There. Number 5, we're going to start talking about lenses. I actually haven't talked about lenses yet, so why would I just start in this? Because the lenses is going to look identical to the mirrors. That's the bizarre thing about it. So it'll actually be quite straightforward if you have that sign convention down pat. We're going to talk about thin lenses, and we're going to treat them just the same way. Okay, a converging lens is a lens that looks like this. And it forms a real image. Here's our object. There's the image, or rather the object distance. And if it's going to be a real image, real image rather, and this is our incident ray, on which side of this thing is the image? Has to be on the side of the outgoing ray. So our image is going to be over here. So this is DI. Real image. Okay. Kind of like that early one we did with the speed of an image. Here's something with the mirror. Here's sort of a similar but different idea. When the okay, so this is DO1, and this is 60 centimeters. And then we're going to move the object 40 centimeters from the lens. So we'll have a DO2. So we'll draw that second situation. Draw it like this, D02. This is 40 centimeters. And then they tell us that the image moves 10 centimeters farther from the lens. So this distance, DI2, is equal to DI1 plus 10. All right. And we know that the focal length of this thing, well, that's actually what we're looking for, I think, right? What is the focal length of the lens? All we know is that it's a converging so that f is greater than 0 is what we know. But our lens equation looks like this. 1 over dO plus 1 over di is equal to 1 over f. This is for lenses. Notice the distinction of this one between that and the mirrors. What distinction is there? There's none. There is one, and it's a very important one. R is not equal to 2f for lenses. So don't get confused with that one point. Okay. So all this information, we're going to have to use this equation a couple of times. One for the first setup, one for the second setup. Hopefully we'll be able to combine them and solve for f. One equation, two unknowns. That's why they gave us two setups. Well, actually, that's two equations and three unknowns. We must need one more. And we've already used it. di2 is equal to di1 plus 10. So there we go. So it's rather suggestive to just do the obvious with this. 1/60th plus 1 over di1 is equal to 1/40th plus 1 over di1 plus 10. Solve for di1. The other way. favorite thing, you got a quadratic. Solver. Or whatever favorite method you have, as long as you have a plan. I don't care. I'm assuming you know how to solve these things. And we find out DI1 is equal to... Did you come up with any solutions, Andrew? Or did you just... 330? Was there 2 solutions? You got the first one you liked and that was it, yeah. All right. $110 and minus 1200. I'm just going to use the web version of this thing. There we go. 1, 10, minus 0. Minus 40 and 30 were the 2 solutions. But now we have to go back and figure out which one fits the conditions that we were given in this problem. We were told something else, how to decide. We were told that it was a real image. Because we were told it was a real image, we must take the positive solution. We were told that the image is a real image. So the
I guess I'm confused as to what direction it's on the right side of the leg. So it might be a negative.
Where's
A negative DI value.
Where's the outgoing light? This is why you have to have that entire sign convention down pat. If you think about the outgoing light, this is a lens, it's not a mirror. The light goes through the lens and goes to there somehow. The light bends. We'll talk about how that ray diagram works in just a bit. So this is the side of the outgoing ray. So on this side, DI is greater than 0. And finally having DI, and we chose the right one, now we can go back and get that focal length using the first setup. 1 over 60 plus 1 over 30 equals 1 over F. F is equal to 20 centimeters. And this had to be a positive number because they also told us that it's a converging lens. So we'll just spend a minute here. Here's our lens. Looks something like that. Here's our object. This will be 60 centimeters. We know that the final image is 30 centimeters. And we know the focal length is 20. So we'll put the focal length on the side of the outgoing ray. Again, positive. And the ray tracing, the rays, how we draw the rays for these lenses. We draw the first ray parallel to the axis. It's almost, it is the same for the mirrors. And then you draw it through the focus. You draw a second ray to this little vertex point. And then you draw it straight on through to the other side. And that's how you find your image. Any questions about the ray tracing construction? We're going to do quite a bit more with those things. What's next? Okay, object is placed 30 centimeters in front of the converging lens. Well, the converging lens have positive radii of curvature. Diverging lens must have negative radii of curvature. Oh, no, that's, well, we got to do 6 first. Let's do 6. So we've got a convex lens, DO. Okay, F is greater than 0. So we know that F is indeed plus 10. Yes. So we can see from the diagram already that the image is real and inverted. So that's where our diagram wasn't terribly accurate, and that's 15 centimeters, plus 15. So it's inverted and smaller. And real. Yes. They're always converging. They don't always form real images. That's a good point. While we're here. So convex lenses are always converging, but do not always form real images. To understand what that's saying, we will put our convex lens here, and we imagine that we have a whole bunch of paraaxial rays. And when they go through the lens, they will go through this point like so. So they converge. So you would always say that all convex lenses are always converging lenses. Now let's take our same convex lens. Those are focus, our focal length is 10. And let's put an object. I'm going to move that focal point out a little bit just to make the diagram work better. Here's our focus. F is equal to 10. I'm going to put an object here at 5. And let's try our ray tracing diagram on this thing. Well, the gain is parallel to the axis and through the focus. Our second ray goes straight through. These rays diverge. The fact that those rays diverge has nothing to do with the fact that it's a converging lens. When we talk about converging lens, we're talking about rays parallel to the axis converging at this point. So since those rays diverge, you trace them backwards. You trace the other one backwards. And you find out your images here. And in this case, the DI is negative, so it's a virtual image. Questions about that? Thank you for bringing that up. It's a real good question because it does cause a lot of confusion. Anyone still confused about that? Exactly. And since it's coming up in the next problem anyway, we'll talk about a diverging lens. Diverging lens is one doing this thing. So if we imagine again our para-axial rays hitting this thing, and the focus in this case is right here, and these rays as they go through are going to go out like so. These are diverging rays. And for this, f is less than 0, always. And what we mean is that the rays act as if they came from this point. And we would call this a concave lens. So concave lenses are always diverging lenses. Actually, sometimes the names get a little more involved. This is often referred to as the double concave. And the other one is called the double convex, meaning both sides have that shape. This one is double concave. All right, let's see what problem 7 is, because it involves a double concave. So an object is placed 30 centimeters in front of a diverging lens. You can think of it like that, f less than 0, with a focal length of 10 centimeters. Here's one of the places where they do just like a confusing thing that you don't want to trip over. They told you it's a diverging lens, and they told you the magnitude of its focal length. You were supposed to put the two together to realize that f is negative 10. Getting clumsy there. And this is our object, DO. The object is 30 centimeters in front of a diverging lens with a focal length of 10 centimeters. What is the image distance? 1 over DO plus 1 over DI equals to 1 over F. 1 over 30 minus, I'll do it the other way. The image distance is negative 7.5 centimeters. Locate the focus and locate the image. Or at least their locations. The focus is negative, that means it's on Well, it's not on the same side as the outgoing light. So the focus is about here. There's the focus. The image distance is negative, so it's not on the same side as the outgoing light. Here's my image. Is the image upright or inverted? Can we tell? Magnification equation would tell us that the image is upright. Magnification is minus di over do, but di is negative, so negative with negative 7.5 divided by 30. At least we know it's positive and smaller. So here's our image. We're doing okay with that? Takes some practice, but it's not too bad. What is the image distance? Remember, I never give you multiple choice, but here's where you have to make sure that you check your answer. They give you both positive and negative choices there. And we know that we want the negative choice. Okay, let's do the ray tracing. Draw a ray from the top of the object parallel to the axis. From the top of the object parallel to the axis. And then, of course, the ray is going to diverge as if it came from the focus. Ray parallel to from the top, and then it goes out as if it came from the focus. A little bit off there. And you trace it backwards. Now you need a second ray, comes from the top of the object and straight through the center of the lens. A subtle but important point, outgoing. Outgoing. These two rays diverge. So what we need to do is trace them both backwards. We already traced the first one backwards. Did that. So now we trace the second one backwards. And that's how we locate the image. That's probably one of the harder diagrams. So we're constructing an array. This one goes parallel to the axis and then out as if it came from the focus. This one goes straight through. Here's our two outgoing rays. But in order to locate the image, you have to find out where the outgoing rays intersect. Well, they don't intersect. So you have to trace them both back. And you trace this one back here. And there you go. So it's actually the fact that we trace this one back is how we know it's at that spot.
Connection of the blue one and the dotted line coming from the top outgoing.
This one here that we trace backwards, and that one there that we trace backwards. Dash lines are kind of messy.
So the second line is like the one coming from the bottom outgoing. That's at different angles than the blue line.
It's supposed to be the same as that blue.
Okay,
I just didn't get it very good. This one right on top of that. Let me see if I can do a better job. Stop it. There you go. A little better. Yeah.
Sorry, so I can ask this.
No,
The red line that you
let me just try to do a better diagram of it. Little. So here's our focus. And what we're doing is thinking of our first ray going to the top. And that's up. And it diverges as if it came from the focus. And we trace that one back. Let's trace that back like so. Now we need to put a second line, and that second line goes straight through here.
The way they connect is the opposite.
That's what I want you to be careful about. It's so tempting to want to do that. I mean, it's a minor point because it comes out to be the same thing as if you did that. But just so that you don't get confused, we're drawing this line here like so. That's pretty bad. This line goes through the center and straight. So what you want to do is recognize that you're thinking of both of those as the outgoing rays. And you've established the fact that these outgoing rays are not going to converge on this side of the lens. We traced that one back already. Now you want to trace this one back. So of course, it does what you think it does. It just goes backwards like here. And then you say, okay, these two things that I traced backwards, they meet right there. And that's how I know that this is the image. It's a minor point, but one to kind of be a little bit careful about. All right. Yeah. How are we doing with these lenses? Feel pretty brave? Okay, we'll skip 8 and 9 for the moment. I'll look it back, but I want to do something. Well, if one lens is so easy to do, now we have to do 2 lenses. So here's a converging lens. F1 is equal to 30 centimeters. And F2 is equal to 20 centimeters. And these two lenses are at distance 70 centimeters apart. And I'm going to put an object 50 centimeters in front of the first lens. And our goal is to find out where the final image is. Again, the sort of questions that we're going to be interested in. Is it real? Is it virtual? Is it upright, inverted? Is it larger or smaller? Okay, step one, find the image formed by the first lens. Those are the lenses. And since they're positive, they're both convex. Yeah. Well, it's a positive focal length, so you know that. It's a converging lens. I just have
not relative to, like, those numbers aren't relative to our line at all.
Right, you cannot get any information about those numbers from the line.
Okay.
But you can put them on there. Not too far off, it'll actually work. Since there's going to be, we've got two lenses, we want to talk about finding the image from the first lens. One over di1 is equal to 1 over f1 minus 1 over do1. So 1 over 30 minus 1 over 50. Which implies that di1, our first image, is at 75. So let's see if we can locate that. Where is the image on this diagram? Andrew. Past the second lens, not very far past it, but a little ways past it. Here's our image. Actually, it would be inverted. Number 1. We're doing okay with that. So now, we need to focus on lens number 2. So we need a DO2. Where is our object? Where is the object for the second lens? It's a -5 because it's on the other side of that lens. So, well, we didn't have negative object distances for mirrors. Here's a situation with lenses where we can have negative object distances. DO2 is equal to -5 centimeters. F2 is 20. So now we find our image. 1 over DI2, our final image. 1 over F2 minus 1 over DO2. 1 over 20 minus 1 over -5. And the image is at 4. Kind of an interesting number. Okay. That's what I got. So now I want to put that in the diagram. Well, 4 is right about there. Is it a real image or a virtual image? It's on the side of the outgoing light, so it's a real image. Light really gets there. Magnification. M total is going to equal M1 times M2. You just get to multiply the separate magnifications. Got enough minus signs there for you? Our final image is inverted and smaller. How do I know it's inverted? Because of that minus sign in the magnification. How do I know it's smaller? Because the number is less than 1. Okay. Ah, was it? I got ahead of myself there. It was 50, so the only place I messed up was here. Greater than 1, okay, yeah. 75, 50, times 4 divided by 5. 1.2, but still negative. Yeah.
Our first image, or non-final, or whatever you want to call it, that is not
My first one was inverted?
They're both inverted. Because the first one would be negative 75.
Correct. They're both inverted. Yeah.
This one bigger, second one.
Yeah. Something like that. Why would you want to do that? Well, this is not particularly a lens combination that's not particularly useful, but we will be dealing with lens combinations in telescopes and whatnot, so it does come up. All right, number 8 has to do with the speed of light. Is that obvious? Just making sure that you have connected index of refraction with the speed of light. Everybody's happy with number 8. All right, number 9. See if we can answer this one. A diver 1.2 meters beneath the surface of a still pond. Okay, no waves. So here's our diver, and he's got a flashlight, and he's saying what angle should he shine the beam of light towards? He shines it at some angle, theta. A person on the shore can see it. So how do you think about that, right? You think we got a person on the shore can just see it, and the light must be going on like that. So you can answer that one pretty quickly. What do you think they're going for? When the refracted light goes out approximately parallel to the surface of the water, you're looking for the critical angle for total internal reflection. And to 2 decimal places, we already know it's that because we already did that one earlier on. So the big question is, what is that number doing there? The diver is 1.2 meters beneath the water. It's a complete distraction. It is only there to cause you to get confused. Okay, next Monday night we're having our exam problem, whichever one it is, but do we know what the subject is? What's the subject? I thought you guys knew what it was. You were nodding your head like you just knew what it was. I should have said, that's it. You know that it's next Monday. You don't know what it's about. Yeah, we're just doing the mirrors, concave, convex, and plane. Don't agree to things that you don't understand. You can get into a whole lot of trouble with that one. All right. See you Monday. Have a good week. And get caught up with everything. We all have to get caught up because the semester is going to come roaring to an end real quick. When's our exam 3? Do you have that in your head? May 8th. which is about 2 to 3 weeks, 3 weeks away, I guess. But you're actually done with